Hey everyone, and welcome to this explainer. Let's jump right into things, shall we? Today, we are going to look at the absolute mechanical titans that drive global trade. I'm talking about those massive marine engines that power container ships across the oceans. But we aren't just looking at any traditional engine today, we're analyzing a real game changer, the WinGD X72DF-A-1.0. And that brings us to the biggest question facing the maritime industry right now. How exactly do you power a massive cargo ship without destroying the planet? Shipping emissions are a colossal global problem, you know. The groundbreaking solution we're examining today is the ammonia-fueled marine engine. It's essentially the ultimate engineering workaround for a carbon-heavy industry. And as you'll see, it relies on some truly incredible mechanics. So here is our lesson plan for today. First, we'll meet the engine. Second, the ammonia revolution. Third, engine installation and dynamics. Fourth, handling ammonia safety. And finally, the engine's digital brain. Okay, Section 1, meet the X72DF-A engine and the scale of innovation. To really wrap your head around what we're talking about here, consider this number, 3,086 millimeters. That's over 3 meters. And get this, that isn't the height of the engine. That is literally just the stroke of a single piston. Imagine a solid chunk of metal the size of a small car moving up and down over 3 meters, roughly 89 times a minute. That's the sheer, staggering scale of the machinery you'll be dealing with as future marine engineers. And that massive stroke, it produces some incredible power, 3,920 kilowatts. But remember, that's just per cylinder. You typically configure these engines with anywhere from 5 to 8 cylinders, depending on the ship's specific needs. Multiply that out, and you have enough raw power to move tens of thousands of tons of cargo straight across the Pacific Ocean. Section 2, the ammonia revolution and its dual fuel capabilities. So the absolutely crucial concept here is dual fuel operation. This engine has the ability to run on either liquid ammonia or traditional marine diesel fuels, and it can seamlessly change modes while running without dropping any power at all. What makes this even possible is the WinGD Flex system. It's an advanced common rail technology that enables incredibly precise electronically controlled fuel injection for optimal combustion. Now, what's genuinely fascinating is the contrast between how these two modes actually behave inside the cylinder. Diesel mode is your standard operation, right? Burning heavy fuel oil or marine gas oil. But ammonia mode relies on a brilliant mechanical workaround. Because ammonia is notoriously difficult to ignite, the main fuel is injected as a high-pressure liquid, but it's ignited by a tiny 5% pilot injection of standard diesel fuel. This pilot flame penetrates the ammonia cloud and literally ignites it from the inside out. It's just brilliant. When you look at the data, it's clear exactly where this giant fits into the wider family of engines. The X72DF-A's operating field occupies a massive, high-power, low-speed block right in the center of the lineup. It is perfectly designed for the heavy, sustained loads required by modern deep-sea cargo vessels. Moving on to Section 3, engine installation and dynamics. Grounding the Titan. You know, you can't exactly just drop an engine of this size onto a standard mount. The foundation isn't just a seating plate. It is a vital structural part of the ship, integrated right into the double-bottom structure. It has to absorb immense torque, vibration, and dynamic forces from both the engine and the propeller. The alignment between the engine and the shaft has to be absolutely flawless. In fact, in certain conditions where the foundation connects directly to the bottom or a cofferdam, classification societies mandate completely watertight bolting. Why? Just to prevent any risk of the engine room flooding. Dealing with those forces is a constant battle. I mean, when you have pistons the size of cars firing, the vibrations are extreme. To mitigate this, engineers use built-in vibration compensators. The integrated electrical balancer, or IELBA, specifically compensates for second-order longitudinal vibrations. They also use integrated axial vibration dampers mounted right on the free end of the crankshaft, which are continuously monitored by oil pressure sensors to ensure the whole system doesn't literally shake itself apart. All right, Section 4, handling ammonia safely and the protocols for toxicity. Future engineers, you'll want to pay close attention here because ammonia's high toxicity makes these ancillary systems literally just as critical as the engine block itself. For starters, all ammonia fuel piping is double-walled. If the inner pipe leaks, the toxic gas is caught in the outer pipe and whisked away by dedicated ventilation to a vapor processing system. To make this safe, the ship requires a massive inert gas supply system, using nitrogen or argon to constantly monitor and purge the lines.
The fuel is managed through a highly secure ammonia fuel valve unit to keep the crew completely isolated from the danger.
And you can't just turn the key, shut this engine off, and walk away. An ammonia normal stop sequence requires some very exact steps. First, liquid purging. Then, backup evaporation and vapor purging. The why here is an absolute safety mandate. Purging the system of residual toxic ammonia with inert gas guarantees that the pipes are gas-free and depressurized before anyone even thinks about doing maintenance. Because of that extreme danger, the rigorous leak testing protocols are absolute. Every single valve and interface is tested under immense pressure before ammonia is ever introduced. During commissioning, it's tested with water at 1.5 times the design pressure. After any component replacement, the system is tested with water pressurized to an incredible 85 bar, or with inert gas. You have to prove the integrity of the system every single time, no exceptions. Finally, Section 5, the engine's digital brain. Enter the WEED system. Modern marine engineering relies heavily on software now. Take the telemetry flow for the WinGD Integrated Digital Expert, or WIDE. Ship navigation data and millions of engine signals are collected on board and then beamed continuously via secure encrypted satellite channels straight to onshore experts and cloud storage. The machine is literally always communicating its status. So what do they actually do with all that data? Well, they feed it into a digital twin. This is a massive trend you're going to see in modern engineering. A digital twin is a thermodynamic model of the exact engine on that specific ship. It's perfectly calibrated during initial shop tests, and then it runs in real time alongside the actual engine. Algorithms measure any tiny deviations between the virtual baseline and actual real-world performance. These algorithms turn that raw data into highly actionable maintenance strategies, basically preventing catastrophic failures before they happen. The WinGD system provides real-time anomaly detection warnings. Say a cylinder pressure drops, it immediately proposes actions for the crew. It allows for live remote troubleshooting with WinGD experts on shore. It even automatically checks the ship's spare parts inventory to make sure you have the right components to fix a problem before it escalates. Which brings us to a final, provocative thought to leave you with. How will digital monitoring and alternative green fuels completely change the role of the modern marine engineer? Your future careers won't just be about tightening bolts on heavy machinery. You are entering a field that is a complex blend of extreme mechanical engineering, highly critical software analysis, and green chemistry. You'll need to master all three to keep global trade moving safely. Thanks for joining me on this explainer. I really hope this sparked your curiosity, and as always, keep learning.